Can can everyone see my screen now? Nice. So hello everyone. It's really great to know everyone here and to deliver some recent um research about myself. Yeah. So at the very beginning, I would like to deliver a very brief self-introduction. I'm Yushun, currently a third-year PhD student from the University of Virginia, United States, and my supervisor is Professor Jundong Li. So in this presentation, I would like to deliver some content about fairness in graph mining. So the main content is focused on the matrix about fairness in graph mining and algorithms about how to mitigate the exhibited bias in graph mining algorithms. And considering that some of you might not be so familiar with maybe fairness notions, maybe graph mining algorithms, so I would like to spend more time on different types of introduction things instead of those technical details in this presentation. So this is a basic outline of this presentation, and basically it includes 4 different parts: the background information, the fairness notions and matrix, the methodologies, existing methodologies to mitigate bias, and also existing problems and future works. So let's first start from the background introduction. So our title is fairness in graph mining algorithms. So the most critical thing is to get a full understanding about graph mining algorithms. So let's first start from an introduction about graph mining algorithms. Actually, as we all know that graph data is pretty ubiquitous across different domains. For example, the social networks, the protein structures, the chemical compounds, and the program flows, they're all examples about graphs in real world scenarios. So as we can see that graphs are everywhere around the world, but how could we benefit from the knowledge encoded in these networks, which could definitely help us to make like predictions on some downstream tasks? So let's take a closer look at the social networks. Let's assume that there is a random person, Jack, and Jack becomes a new user of this social networking platform. So a natural question is, who should be recommended to him? And if we take a closer look at Jack, after the first week, Jack chose to become a friend of Sarah and Erastus, which is two person that already exists in this social networking platform. And another natural question is, who else should be recommended to him? So they're all critical questions because how do you answer these questions directly determines the user experience about your social networking platform. So we have to make accurate and efficient predictions for those new users in the social networking platforms. And that's what graph mining algorithms help us to do. In summary, graph mining algorithms are algorithms that extract information encoded in the graph data in order to facilitate our understanding of these graph data and also gain benefit on various predictive tasks. For example, for those graphs we have seen before, after the graph mining algorithms, we might be able to answer the question like, who are potential friends in a social networking platform, and what will the properties of the certain chemical compound be like, or like which part of the protein will account for its interactions with other chemical compounds. So this is a basic overview about what is graph mining algorithm. And the second question is, what is fairness? Actually, fairness is a very vague notion because there is no specific or general criterion or universal criterion that defines how to determine whether the fairness has been fulfilled or not. For example, we might be familiar with two different notions, which is equality and equity. However, it really depends on the specific application scenario for you to determine whether equality or equity should be considered as fairness. So despite that we do not have a universal criterion to fulfill fairness, we could still do fairness study. And this is because there are various existing fairness notions based on people's awareness. For example, let's assume that we have a group of different people, and these different people might participate in different types of application scenarios. For example, they do loan application, they participate in the social networking applications, they might follow each other on Twitter, they participate in different types of applications that is based on graphs. And based on people's awareness, researchers have defined various of fairness notions. For example, the equity and equality we have seen before. And the problem is, for a certain existing fairness notion that has been defined by the researchers based on the people's awareness in real-world scenarios, how could we realize them in algorithms? So basically, that's the workflow for the fairness-related research in tabular data, which is pretty popular in traditional data mining. But in graph mining, we will have graph-based application scenarios. And based on people's awareness, we could have some traditional fairness notions that could be applied to these graph-based application scenarios. And also, based on the characteristics of your graph data, we might also have some novel fairness notions that is not studied or defined in traditional graph mining on tabular data. And the question here is similar, which is how could we realize these fairness notions in graph mining algorithms? So this is a basic introduction about fairness in traditional traditional data mining algorithms and fairness in the realm of graph mining algorithms. So in the second part, we will focus on different types of fairness notions that is defined by researchers based on people's awareness in real-world applications. And still, we will introduce those matrix, like how could we quantitatively measure to what extent a certain fairness notion has been fulfilled or achieved. So in one of our previous survey paper, we proposed a taxonomy of those commonly used algorithm fairness notions in graph mining algorithms. As we can see here, we have group fairness, we have individual fairness, we have the degree-related fairness, counterfactual fairness, and application-specific fairness. Due to time limit in this presentation, I would focus on the first three fairness notions, which is the most critical ones in the realm of graph mining. And if you're really interested in like maybe more details about the techniques or the other fairness notions, you could refer to our paper, which is the second reference here. So let's first start from the group fairness. So general idea of group fairness is that first, we have some categorical sensitive attributes or sensitive features. For example, we have gender, race, and these categorical sensitive features will divide the whole population into different demographic subgroups. And group fairness emphasizes that each group should gain their fair share of interest. As we mentioned before, what is fair should be further instantiated, and what is interest will depend on specific application scenarios. But we have some default settings, and I will introduce in the following slides, like what is interest. So the first fairness notion, which is the most widely studied one in group fairness, is demographic parity. So demographic parity is first proposed in binary classification tests for tabular data, which is like traditional data mining algorithms in like this paper. And demographic parity is considered as achieved if the model yields the same positive rate for individuals in those sensitive subgroups. And like these subgroups is divided by the categorical sensitive features, as I mentioned before. And let's take the gender here as an example of the sensitive feature. And obviously we have two groups. The first group is the female group, and the second group are male group. So let's assume that we have a binary classification for them. For example, they're applicants for a loan, and we're trying to determine whether their loan application should be approved or not. As we can see that in this case, if we have assigned the decisions as follows, we have a positive rate, which is the approval rate for both groups as 50%. So in this case, we have the same positive rate across the two groups. So this should be considered as fair in perspective of the demographic parity. However, in another case, as we can see that in female group, we have a 50% of the approval rate. However, in the male group, we have 75%. So in this case, actually, male group is favored. However, female group is kind of discriminated. So that is not what we want. So this should definitely be considered as an unfair case in perspective of demographic parity. Correspondingly, we have the mathematical criterion as follows. Conditional on the binary sensitive feature, we should have the same probability to come to a positive prediction across the two groups. And this would be the criterion. But of course, the criterion is, really hard to be fully achieved in real world scenarios or even in some simplified downstream tasks. So we should definitely have a matrix to measure like to what extent demographic parity has been achieved. And the matrix is also straightforward, which is directly the difference between the probabilities of coming to a positive prediction across the two groups. So because this is the most important and widely studied fairness notion in group fairness, so I summarized some very interesting takeaway points about it. The first interesting takeaway point is the demographic parity notion is defined in binary classification tests for tabular data in traditional data mining tests. And there should definitely be categorical sensitive features which could divide the whole population into two different sensitive subgroups. And the second thing is that, as you can see, we haven't talked about anything about ground truths. We only talk about like positive predictions and sensitive features. So actually for this notion, it does not consider the ground truth labels. So as a consequence, enforcing this kind of fairness notion, the demographic parity, may lead to sacrifice on your model utility in practice, but not necessarily sacrifice. Sometimes it will sacrifice the utility. And the third takeaway point is recent works on fairness have extended the notion of demographic parity to other settings. I mean, binary classification is really a really limited setting. So we have actually extensions in link prediction tasks in graph mining, and also scenarios with continuous sensitive features, which extend the categorical requirement. Yeah. So this is the introduction about demographic parity, which is the most widely studied group fairness notion. But beyond that, we also have other popular group fairness notions. And here I bring a comparison between the equality of odds and equality of opportunity. So both of the two fairness notions here is proposed in the 7th citation. And specifically, the equality of odds emphasize that the positive rate should be the same across the two demographic subgroups, conditional on the ground truth class tables. And the intuition is that we aim to enforce the true positive rate and the false positive rate across to be the same across different groups. So here, an intuition is that for the author of this paper, he argues that a positive outcome should be considered as beneficial for those involved individuals. For example, the admission to the university, the approval of your loan application. So across these settings, a positive prediction should be considered as beneficial ones, and we should really treat the positive predictions carefully. So the intuition about equality of odds here is to enforce the right and beneficial results and wrong but beneficial results to be the same across the two groups. And the two types of results corresponds to the true positive rate and false positive rate corresponding. And the other fairness notion is the equality of opportunity. So the equality of opportunity actually reduces the requirement compared with the equality of odds, where this fairness notion only enforces that the positive rate should be the same across the two demographic subgroups, conditional on the positive ground truth class tables, which means that we do not enforce the second one. So the basic intuition is that we aim to enforce the right and also beneficial results to be the same across the two groups. Actually, the notion of equality of opportunity is more widely studied in graph mining tasks, for example, node classification. And we have corresponding criterion here, like mathematically, we should enforce the probability of coming to a positive prediction to be the same, conditional on your sensitive feature, and also conditional on your positive ground truth label. And correspondingly, we could formulate the matrix to measure to what extent the EO has been achieved, which is very straightforward to compute the difference between the two types of probabilities. And also, equality of opportunity is very popular, so it has been extended to different tasks, like tasks other than node classification, for example, link prediction. And now we come to a different fairness notion, which is the individual fairness notion. So from the group fairness notion to the individual fairness notion, we really have to shift our mind, because in individual fairness, we do not have any sensitive feature. But a general idea of individual fairness is that similar individual should be treated similarly, which means that similar individuals should receive similar output from the graph mining algorithms. So it's basically an individual level of fairness. The first type of individual fairness is the node pair distance based fairness. The basic intuition here is that for any pair of node, their fairness notion, this fairness notion aims to enforce the output distance to be similar or equal to a scaled input distance, which is consistent with the general idea of similar individuals should be treated similarly. So mathematically, we could formulate this kind of requirement as follows. We have a f function, which is the graph mining algorithm. As you can see that we input an instance, and out with the f function, we output the corresponding prediction of the input instance. And by using D1, we measure the output distance between the prediction of instance X and instance Y. By using the function D2, we measure the input distance, which is the like the dissimilarity between the instance X and Y in the input space. And we still have an L here, which is a scaling factor. But this kind of formulation is, I believe it reminds you the Lipschitz condition. So the L here should be the Lipschitz constant. So I'm sorry for the mistake here. And in graph mining, in practice, we could definitely enforce the following inequality to enforce the no pair distance space fairness. So here we enforce the Frobenius norm of the distance between those output logics. And the Sij here should be considered as the similarity score between the ith instance and jth instance. And the similarity score measures how similar the two instances are in the input space. And usually these similarities should be considered, should be given, these scores should be given by a domain experts, which determines like how similar should we consider two persons are. And the second type of individual fairness notion is a node ranking based fairness, which proposed by like our research group in one of our previous paper. So basically, this fairness notion enforces that for every individual, we should have exactly the same ranking list when we consider its similarity with other individuals. For example, let's consider we have a similarity matrix based on your output, which is y hat. And we also have a similarity matrix, which is SG. And the similarity score here should be given by domain expert. And correspondingly, for a specific user to be focused on, we will have its similarity between this user and other users. And we will have this kind of ranking list for in both similarity matrix. As we can see that for these node pairs, we have an inconsistent one, but for others, we are those node pairs are consistent. However, node ranking-based fairness aims to enforce the ranking between those node pairs to be exactly the same in across the input space and output space. So the criterion is that, for example, we have node U1, and the similarity ranking between this user and other users, for example, is 4, 3, 2, 5. And this fairness notion aims to enforce that for this user in the output space, the ranking should also be 4, 3, 2, 5. And correspondingly, we could have matrix to measure to what extent this kind of ranking-based fairness has been achieved. For example, we could compute the average ranking similarity across all individuals. And for each individual, we could measure the ranking similarity with, for example, the average, the NDCG at K. And K here is basically determined by how focused on like the truncation length of the top ranked nodes. And for the third fairness notion, we would focus on the degree-related fairness. So for the previous two fairness notions, including the group fairness and individual fairness, they're basically also studied in traditional fairness, in traditional data mining algorithms in tabular data. However, those degree-related fairness is coupled with your input graph data, which means that this is novel fairness notion in the realm of graph mining compared with those traditional data mining on tabular data. And a general idea of degree-related fairness is that the degree of nodes should be independent from the quality of their corresponding predictions received from the graph mining algorithms. But why do we have to achieve the fairness across to the degree? In other words, why this kind of bias arise naturally in your graph mining algorithms? For example, there is a very widely known mechanism in graph mining algorithms, especially in graph neural networks, which is message passing. Basically, what we do in message passing is to enforce the neighbor of a studied node to contribute useful information to the studied node, which is the target node A here. By doing this, we could have complementary information about node A, and after the propagation, we could make more accurate predictions corresponding to this node. So actually, this reveals that in graph data, a critical source of useful information for you to do predictions is the complementary information between a node and its neighbors. However, if we do predictions for those nodes and do like a plot about the accuracy and degree, as we can see that we could have a very clear tendency, and this tendency is basically caused by the difference in the neighbors corresponding to each node. And this is because in graph mining algorithms, they rely on a node's neighbors to contribute complementary information, and we could then do more accurate predictions. However, for nodes with high degrees, of course, it has like more neighbors, and it could receive more complementary information for you to do more accurate predictions. However, for nodes with very low degree, for example, 0 or 1, they do not have that many neighbors to contribute complementary information to the study node to help us to make more accurate predictions. So of course, we will have a higher average loss and also a lower average accuracy corresponding to those nodes with low degrees, or we see with fewer neighbors. So this naturally causes there could be degree-related fairness problems in graph mining algorithms. And just a reminder that this kind of degree-related fairness notion requires that those nodes should bear similar utility in the graph mining algorithms, regardless of their degrees. And so these are the basic fairness notions. Actually, the 3 most widely studied one, and its corresponding matrix. So in the following section, I would like to introduce some methodologies to mitigate these bias. So still the taxonomy proposed in one of our previous survey. In general, there are 6 main categories of the most commonly used techniques to improve the fairness in graph mining, which includes the optimization with regularization, optimization with constraints, and adversarial learning, edge rewiring, rebalancing, and orthogonal projection. So let's start from the optimization with regularization. As we can see that this is a basic data flow of the optimization with regularization. And basically what we do is to directly add a fairness regularization in our algorithm. And as we can see that after we have added the regularization in the solution space, we will have like places that are more unfair, and we will have places that are fairer compared with those unfair places in the solution space. And mathematically, we could really add a loss term, a repeated loss term on the total objective function. And this kind of fairness-aware loss term could be formulated in different ways. For example, there are existing works formulate the regularization term based on the output logics, based on the network topology, and also based on node embeddings. So a very straightforward intuition is that if we could achieve fairness, then the node embedding should also bear similar distributions. So this is a very straightforward regularization. Yeah, so another very straightforward formulation is maybe you could directly add um the 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 matrix we have introduced before. This is really straightforward, but this is not differentiable. So if you like to solve a optimization problem with gradient descent based techniques, maybe you could not do that. But if you could solve some discrete optimization problems, maybe you could do that. And the second methodology is the optimization with constraints. We can clearly see the difference between these two methodologies. When adding your fairness-aware constraint to the model, we'll have a clear boundary between the fair model space and unfair model space. So mathematically, we could directly add a fairness-aware constraint to your optimization problem. So initially you have a loss about your utility. You would like to minimize the loss about your utility. But now we should subject to some certain fairness constraints. There are also straightforward ways to formulate such a constraint, and most existing works directly formulate this constraint based on the performance difference on different demographic subgroups. And of course, this should be considered as the strategy to mitigate the bias in perspective of group fairness. And there are also actually other ways to formulate this kind of fairness constraint under other fairness notions. And if you're really interested, you could refer to our paper, survey paper. And the third methodology is the adversarial learning. So this is a very interesting method and also widely studied and used in different types of graph mining algorithms for debiasing. Generally, we have a generator and discriminator in this methodology. Here, the generator has two different tasks. And the first task is to generate embeddings that are informative for you to do accurate downstream task predictions. And the second task is to generate embeddings that are without sensitive information. In other words, the embeddings should be decoupled from your sensitive features. And the embeddings here are generated and fed into the discriminator. And the sole goal of discriminator is to try to distinguish the sensitive feature corresponding to each data instance and predict their sensitive feature. So after the adversarial learning process, the discriminator can no longer distinguish the corresponding sensitive feature of those data instances. And now we could say that, okay, those embeddings are without those sensitive information. But still, because one of the goals of the generator is to generate informative embeddings to do accurate downstream tasks. So we could still achieve very good utility performance. And the methodology in the following part is the edge rewiring. So here, very insightful knowledge is that the input data of those graph mining algorithms could also be biased. So maybe debiasing in the pre-processing stage about the network data should also be considered. So edge rewiring here is a kind of that method. More specifically, as you can see that we have an input graph and we do some kind of edge rewiring with respect to some certain goals to debias. And then we could input the debiased network data into your graph mining algorithm. And you could consider to achieve accurate downstream task utility, but still low level of bias. So basically what we do here is try to rewire the edge in order to like prevent the bias encoded in the network structure to influence the algorithm and also the output for the downstream tasks. So there is a very intuitive example about biased graph structure. So a biased structure, graph structure could look like in different, could be like in different patterns, but a very straightforward and 2-to-1 would be look like this. So as you can see that there are very clear community structure between two groups of nodes, the yellow group and blue group, where the membership is basically depend on the sensitive features corresponding to each node. Actually, for those widely adopted message passing mechanisms, which is adopted by different types of graph mining algorithms, once you conduct the message passing mechanism on such kind of biased graph structure, this kind of bias will also be exhibited in the propagated node embeddings and finally influence the downstream task predictions. So this methodology is also useful for you to achieve debiasing for downstream task outputs. And another methodology here is the rebalancing, but rebalancing here is also vague. Actually, rebalancing could also be achieved in different ways, depending on the characteristics of the graph mining algorithms and your tasks. So basically, this is a very general data flow of what rebalancing will look like. As you can see that we do rebalancing in the algorithm in order to achieve a very balanced distribution. And finally, we could have more predictions with less bias or more fair predictions. And an example of the rebalancing here is a modification on random walk algorithms. As we'll know that for some network embedding problems, we could do random walk to generate sequential instances about the connections between those nodes. And then we could learn embeddings based on those sequences. But these embeddings we learn could be biased. And this is because for a certain node, it could link to nodes with different types of membership depending on their sensitive features. However, as we all know that, for example, a node with a certain sensitive feature might tend to connect with other nodes with the same sensitive feature. So if we carry out random walk on these type of graphs, the learned node embeddings might be biased because of the constraint of those existing edges. For example, let's assume that we have a study node here, and this node connects to a male node, but two female nodes. If we still consider an even distribution across these edges for the probability of the transitions, we will have higher probability of connect the male node to a female node instead of a male node. But still, we would like to achieve a fair node embedding. So what could we do? A straightforward way is to really change or rebalance the transition probability across these two demographic subgroups. For example, we could rebalance the transition probability between these study nodes to female links to be 1/4, and we could rebalance the male to male transition to be like 50%. So after this rebalancing, we could achieve a goal, which is enforcing the transition between this node and other nodes to be the same over different types of demographic subgroups based on their sensitive features. So this is also a really interesting algorithm. If you're interested, you could refer to this citation. And the last methodology to mitigate bias is also interesting, which is the orthogonal projection. So this is a general data flow of the orthogonal projection. So as you can see that we have an input graph, and finally after the algorithm, we have the output embedding. However, the embedding could be biased across maybe two demographic subgroups. So what should we do? Actually, what we could do here is to find a hyperplane which is orthogonal to the direction of the exhibited bias in the node embeddings. And now what we do is to project the node embeddings onto this hyperplane that is orthogonal to bias. So after we have done that, we could guarantee that there will be no correlation between our learned node embeddings, like the projected embeddings, and the direction of bias. So here's a very interesting example. So we could we have a set of node embeddings, and let's assume we have maybe 2 different groups. And we could first compute the average direction of a unit vector within each demographic subgroups. And we will have Z average 1 and Z average 2. And now we would like to find the bias direction, which is the deviation between these 2 unit vectors. And it could be computed like this. And now what we do is to project all node embeddings onto a hyperplane that is orthogonal to this bias direction we have found. And it could be achieved by this. So by doing this, we could achieve that the projected Z prime do not have any correlation corresponding to the bias information we have found before. But the no correlation here definitely means the no linear correlation. So this paper actually does not handle the problem of maybe high order correlation, high order dependency between the projected node embedding and your bias information. And in the last section, I'd like to introduce some existing problems and maybe future works. So the first problem is the lack of fairness notions. You might argue that, well, we have introduced so many different types of fairness notions. Why we still lack fairness notions? So a natural problem is that can existing fairness notions help to avoid all cases where people may feel unfair? So basically, the motivation to propose a new fairness notion is that, well, maybe you could observe a case where people will get a sense of unfair, and you could be motivated by this kind of case and say maybe, oh, well, some people may feel unfair in this case. So definitely, of course, we should propose a fairness notion to avoid such case where people may feel unfair. But existing fairness notions cannot guarantee to avoid all cases where people may feel unfair. So for those potential cases, people could still feel unfair. There's still room for us to propose novel fairness notions. And the second existing problem is to fulfill multiple types of fairness. Well, a straightforward question might be how to achieve multiple types of fairness in one algorithm. But a more in-depth question is, are some of the existing fairness notions actually in conflict with each other? And this is also a problem that is quite worth in-depth exploration. And the third sub-question here is that if we could achieve multiple types of fairness, will people get a stronger sense of fairness? Actually, might be not. So if not, what will be actually beneficial for social good instead of like solely achieving multiple types of fairness? And the third existing problem is the balancing between the model utility and algorithm fairness. As you can see that apart from the equal odds and equal opportunity, we barely mention anything about ground truth labels in those classification tasks. So actually for those fairness notions, they do not consider anything about the ground truth labels. So actually they bear a different goal mathematically compared with your model utility. So in most cases, if you would like to fulfill algorithmic fairness, you might sacrifice some of the model utility. And the natural problem is how to achieve fairness at low cost of utility or at no cost of utility. And the fourth problem here is the explanation or interpretation about how unfairness arises in those graph mining algorithms. So we have sub questions here as maybe how to interpret why those unfairness arise in graph mining algorithms. Maybe we could have insights about, is the graph data biased or is the model biased naturally? Actually, there are already some existing works reveal that the graph data could the exhibited bias might be encoded in the input graph data of your graph mining algorithms. And during learning, the model could also be biased too. And the last question is enhancing the robustness of algorithms on fairness. So here we consider like those graph mining algorithms could be attacked in perspective of fairness by maybe malicious users. And we're actually wondering that how would those existing graph mining algorithms perform under those malicious attacks? And if that attacks really happen, how could we achieve better robustness in the perspective of fairness in order to achieve fairer predictions under those attacks? And here are the references, including maybe all the interesting papers we have mentioned before. And that's all for my presentation. Thanks for listening. I think we still have 10 minutes to handle the questions from the audience, and I will be more than happy to answer any questions. Thank you.